now we're going to look at the available rotational energy to a dipole when it sits in a uniform electric field, and we're going to do that by looking at the torque and how much availability is there for torque to act to align the dipole with the electric field. Now, when the dipole sits in this position shown in our first diagram up top here, so that the dipole moment vector P is already aligned with the electric field. So when we do P cross E, what we see is that we get no torque. So not only do we get no torque, this is important, so make sure you get all of this in your notes. We are in stable equilibrium. So even a small disturbance in the P, so if we took the positively charged and the negatively charged and just rotated that P vector up a little bit, yes, it would swing back down and align with the E field, and it would oscillate back and forth on that E field. But really, we don't have a lot of available energy. There's essentially no available energy when it's in-aligned, and even if we disturb it, we have essentially minimal potential energy available to us. So this orientation is going to correspond to our potential energy min. So let's get that down, and hopefully that makes some sense. Well, what would be the maximum ability for the torque to act to allow the torque to continue to accelerate the particle with an alpha to give it kinetic energy? Well, that orientation is shown here. So if the P vector and the E vector are anti-parallel, or 180 degrees to us, at this specific point, yes, indeed, we do get no, torque. However, there's a lot of available energy. We are in unstable equilibrium. Even a small disturbance causes a large rotation, because once that P vector is even pulled up or pulled down a little bit, it is going to rotate all the way through, and you'll get an oscillation, big oscillation, right, between the top and the bottom. Lots of rotational potential energy here made into rotational kinetic energy as it goes to align, and we'll talk more about the details of what the equation looks like on our next page of notes, but for right now, PE max. Well, the other important orientation for us to look at and understand is this halfway point. So again, by way of torque, we can see that we have a maximum torque, right? So this is where energy and torque kind of diverges a little bit for us. A maximum torque right at 90 degrees. However, we are certainly not at the maximum ability to rotate. We're actually at a halfway point to rotate. So that is why I have that this is the halfway potential energy point, and as I had said, please make sure you get this into your notes, even though the torque is a maximum, but not as much rotation to align with the E field, so we're at our halfway potential energy point. So let me zoom out here for a moment. I know it's a relatively short page of notes, but I think conceptually just wrapping our minds around this will help us out when we look at our derivation for potential energy and start getting very mathy with our understanding of potential energy. This should help us out.